In this lecture, I'm going to tell you a little bit about a project that I lead called the Large Synoptic Survey Telescope. It's a very large project. It will be funded by the National Science Foundation, the Department of Energy, and it's also benefited from a lot of private funding. I've been working on this project for something like 10 years. We're just going into formal construction this year, assuming that the government doesn't shut down once again. I will try to convey to you some of the excitement behind the project and what's new about it. So actually, the idea behind LSST, or surveying the universe in general, is extremely simple. Build a very large telescope that can take large format images of the sky, of a large area of the sky, and do that quickly so that you can step through the sky and cover the entire southern sky every few nights. And then we do that repeatedly for 10 years. Very simple idea. But the scientific implications are profound, and that's what I will try to convey to you in this talk. In particular, we'll measure everything that moves in the sky. Asteroids, comets, stellar parallax, which is the motion of stars, the apparent motion of stars as the Earth makes its annual orbit around the sun. We'll measure everything that varies in time in the sky. Variable stars, supernovae, quasars, gamma ray bursts. And then we can add all of those exposures, and we'll have something like 1,000 or more exposures of every part of the sky over the 10 years. We can add them all together and obtain extremely deep pictures of the entire universe. And as mentioned, we'll measure billions of galaxies out to the edge of the universe. In fact, the observable universe only contains about 100 billion galaxies. And LSST will detect about 10 billion. So 10% of everything that it's possible to see in the universe will come from this project. So why is this a new thing? We've been doing astronomy. Humans have been doing astronomy for hundreds of years, built lots of telescopes along the way. But in fact, we've only looked at a tiny piece of the sky. Basically, the sky is a big place. And most of the telescopes that have been built to date have relatively small fields of view, so they can only take pictures of a tiny part of the sky at any given time. And given the size of the sky, it would take hundreds and hundreds, maybe even thousands of years to cover the whole sky with conventional technology. What makes it possible to do this now is something called the étendue of the telescope. The étendue, in its simplest form, is the product of the collecting area, how large is the mirror that you collect the light with, times the field of view. How big a region of the sky do you cover in every single picture? So this slide sort of illustrates this. There are two facilities shown on the slide. The first is something called the Gemini South Telescope, which is actually it's one of the largest telescopes that exists today in the world, has an 8-meter primary mirror. And it happens to be close physically to where LSST will be sited. And on some scale, this is an indication of the size of the Gemini South Telescope. And this is an indication of the field of view. For LSST, the size of the mirror is roughly comparable, actually even a little bit smaller because it has a hole in the middle, and I'll tell you why that is later, to Gemini South. So it's not necessarily a bigger telescope, but on the same scale, this is the field of view. In fact, this field of view is about 40 times the size of the full moon in the sky. So if you imagine looking up at the full moon and drawing a circle that's 40 times bigger, that's a single picture from LSST. And we will take a picture like that every 15 seconds for 10 years. So that's what enables us to cover such a large part of the sky. And it's the product of this times this that is the étendue, and that's related to how much light does a telescope collect as a function of time, or how quickly can you survey the sky? And that's what's new. Now, in fact, doing wide field imaging of the sky itself is not new. This is a drawing of what's called the Palomar-Schmidt telescope, which was built by Caltech in the early part of the 20th century, and did a heroic job during the 40s, 50s, and 60s in mapping the sky. But the Schmidt telescope used large photographic plates to take those pictures. So the plates were quite large. And they made maps of the skies that showed us where all the bright stars were in the sky. And those maps are still used today to find things in the sky. We make finding charts by taking pictures, small pictures of those plates, and then we can identify the stellar structure and find out where we're pointing. But photographic plates, as you're probably aware, are not especially sensitive. So in order to go deep, in order to get faint pictures of the sky, you would have to expose for extremely long periods of time, in fact, longer than a night. And so the early kind of surveying that had been done in previous decades got us the brightest objects of the sky, but not things that are very faint. In order to go deep, we need highly sensitive electronic detectors, things like charge-coupled devices or CMOS devices, which are the sensors that are inside the digital cameras that most of you probably have, or even in your cell phones. So these have been available for astronomy since about the late 1980s. And industry has gotten better and better at producing larger and larger such devices with higher sensitivity. Now, the étendue that I talked about earlier, this product of the collecting area and the field of view, is roughly proportional to the physical size of the detector. So in order to have high étendue, in order to be able to survey the sky quickly, you need a physically very large detector. And so this plot, which I'm showing you, this is sort of all the previous surveys that have been done to date in both the optical band and this is the infrared band. So the vertical axis here is how large a region of sky was covered in the survey, and the horizontal axis is how faint did that survey go. And so you can see some of the previous surveys covered a lot of the sky, but they didn't go very faint. Others, like for example, this is the Hubble Deep Field and the Ultra Deep Field, which were performed by Space Telescope. Those went extremely faint, but they only covered a very small fraction of the sky. And so if you look at these plots, you'll notice there's kind of an envelope here, which is roughly indicated by this red line. That's a line of fixed detector size. Okay, so the same size detector could be used to make a survey that doesn't go faint but covers a lot of sky, or a survey that goes very faint and covers a small part of the sky. It's roughly a fraction of, how much time are you spending on each part of the sky. In order to get higher étendue, in order to go deeper and make these large surveys, we had to head out in this direction. This is a logarithmic scale. This is where LSST is, and there's nothing that's been close to it before. So that's what's new about it. And I'll tell you a little bit more about the technology later. So this is not a real picture. It's a simulated picture. We have a rather advanced simulation tool for this telescope to predict what we're going to see. You can see all the detail in this picture. This is 1/200th of one 15-second picture. Okay, I could not display a full LSST picture on a screen where you would be able to see all the individual objects just because it's too large. In fact, it would take something like 100 or 200 high-definition telescopes, high-definition televisions to display one LSST picture at a resolution where you could actually see the things. And so you can see how many stars and galaxies there are when you get to this depth. There is something like 40 or 50 galaxies for every arc minute of sky, an enormous number of objects. So when we make a survey like this, one of the things that immediately should jump to your attention is we're going to produce an enormous amount of data. And I'll come back to that later. We talk about some of the challenges. Okay, this is a big project. When you count the operations costs and everything else, it'll be about $1 billion total. The construction alone is $650 million. About 400, some of that will be funded by the National Science Foundation, and the remainder is funded by the Department of Energy. Now, those kinds of investments in a pure science project don't happen easily. You have to go through many, many reviews, jump through many hoops. That's the reason why I've been working on this 10 years, and we're only starting the official construction now. The government puts you through all kinds of tests before allocations of this kind of money happen. But one of the things that got us going is that the astronomy and astrophysics community in the United States every 10 years undertakes what's called a decadal survey or a decadal investigation. They convene many, many scientists from all over the country together into panels to discuss what are our priorities for the future, what are the big scientific questions that are pressing for the next 10 years, and what sort of facilities should we build. And so every 10 years a report comes out. The last one came out in 2010. It was called New Worlds, New Horizons. So this is a synopsis from the entire community of astronomers and astrophysicists about the highest priorities. And in this report, LSST was ranked as the highest priority large ground-based facility for the next decade. That was the kind of endorsement we needed to get this officially through with the government. And one of the things that I'm personally most proud of, having been involved with this for a while, is that that top rank, this is a quotation from the report, the top rank was accorded not only because of the compelling science and the capacity to address a huge number of science goals, which I'll go through in this talk, but also because of the technical readiness of the proposal. We'd been doing a lot of work on this project. We had a very mature design. We'd prototyped most of the key elements. And in the view of this report, this project was so-called shovel ready, ready to build. And that's what's allowing us to move forward with it now. So at this point, I'm going to take you on a little bit of a tour through the range of science that you can do if you really try to survey half the sky at the kind of depth that we will achieve. As I mentioned, we'll get something like 1,000 observations of every part of the sky, which means we'll see everything that's changing. And one of the most obvious things that you find when you do that is that there's lots of things moving across the sky. Most of those are asteroids. So these are real pictures, actually, from another facility. So this is a picture taken at 5 hours, 54 minutes, and 11 seconds. Here's a picture taken at 6 hours, 44 minutes, and 31 seconds, the same part of the sky. You can see they're different. When you subtract the two, all the stars and the galaxies drop out of the picture, and you see this kind of positive-negative feature. So there's a negative blip here and a positive blip here, and that means that an object has been moving through the sky. Okay, so it's in one place in the earlier frame and another place in the other. This is an asteroid, and this is a pretty simple idea. This is how we detect asteroids. You take two images close in time to one another, subtract them, and look for the differences. Everything that's constant will have stayed unchanged and subtract out, and the things that are moving will show up this way. So those will give us all the asteroids. And we will detect millions and millions of asteroids. And you might think, so what? Why are those interesting? It's a large population. Because we'll have many, many exposures, we'll not only find these asteroids, we'll also have enough measurements of where they are and where they're heading that will actually solve for their orbits. There are millions of objects, and we know their orbits. And you can make a plot like this. This is actually a plot. This is real data from an earlier object. So it's plotted here on the vertical scale is the sign of the inclination of the orbit of that asteroid relative to the solar system plane. And on the horizontal scale is the distance of that asteroid from the sun, the center of the orbit, or some position in the orbit. And the colors on this plot are meaningful. The ones that are blue or red or green or yellow, et cetera, actually have different appearance. So the color that an asteroid looks like when you take pictures of it in different bands is related to what's called the albedo of the surface, so sunlight reflecting off that asteroid. It depends on the chemical composition of the surface, et cetera. So with these millions of asteroids, it's a much, much larger database than this is. We'll have all these colors, so we'll be able to plot them like this. But for every single point on a plot like this, we'll be able to trace its orbit both forward in time and backward in time. Some of this has been done already with much smaller samples. And what you find is if you take the blue points and you trace their orbits back in time, they actually come together at an early point in the solar system's history. Similarly for the red points, the green points, etc. Why is that? It's because all these asteroids started out as much larger objects in the solar system, and then over the history of the solar system, those objects collided with one another, they fragmented, and they populated the solar system with this vast array of moving objects. So tracing this is a way of essentially cataloging the history of the solar system. Something that's really fascinating, understanding how the solar system first formed from a disk of gas to individual planets, to the smaller objects, etc. Now, one of the interesting and perhaps more practical aspects of this kind of work is paying attention to the particular class of asteroids that are called potentially hazardous asteroids. Why are they potentially hazardous? Because their orbits are such that they could intersect the Earth. And if a large enough asteroid intersects the Earth, it can do a lot of damage. So this is a plot of the number of asteroids, notice it's a logarithmic scale, as a function of the size of the asteroids, also a logarithmic scale. And the distribution of these rocks, which is not terribly surprising because they're produced by fragmentation of larger bodies, looks like a power law on the plot. In other words, there's a huge number of very small ones, and there's a small number of very large ones. Okay? There are some other scales on this plot. So this is physical size, diameter. This scale is related to how bright the asteroid is, which of course is the bigger objects are brighter because they reflect more of the sunlight. And the top scale is called impact energy, and the units of that are megatons of TNT. Okay? So this is, and again, this is a logarithmic scale. So one of these guys, if it were to impact the Earth, would be like a 100 megaton bomb. That's big enough to do serious damage to all of civilization. Fortunately, there aren't all that many of these guys. This one is, what's indicated here is something called the KT impactor, which is an event in the distant past that we find evidence of on the Earth. Had a major impact on the populations of species on Earth at that time. Now on this plot, the red line is the really interesting thing. This is essentially our knowledge of, meaning explicitly, which objects are there and what are their orbits as a function of their size. So these really big guys are very worrisome, but fortunately, we know essentially all of them. And there are none that are going to hit in at least the next few thousand years, as far as we can tell. So this is interesting to talk about, but it's not a real threat. But you'll notice as you go to smaller objects, the red line turns over, and in this regime, actually our knowledge of the asteroid population that could hit the Earth is really rather small. It's only a few percent or so. These guys are still pretty dangerous. So this is roughly 100 meter in size, 100 meter rock. Now that size range is large enough such that an asteroid like that will not burn up or disintegrate in the atmosphere. It will actually make it all the way down to the Earth's surface. If you go much smaller than that, these things, which are extremely numerous, for the most part, disintegrate in the atmosphere and do relatively minor, if any, damage at all to Earth. So it's these guys that are the most concerning because they can do damage and because we don't know where they are. And what's the most likely form of damage that they'll do? If you ask people that question, most people think, well, it'll hit a house or it'll hit a city, whatever. But if you look at the surface of the Earth, I'm sure most of you are aware, only a very small fraction of the Earth's surface is actually populated. So in terms of the solid Earth, if an asteroid impacts, the most likely thing it will happen is it'll fall in an empty field, maybe cause some ripples, but otherwise not too much damage. It's actually more serious if a 100-meter asteroid falls into the ocean. A 100-meter asteroid falling into the ocean will almost certainly create a worldwide tsunami. And so it's damage to coastal areas that's the primary threat from this kind of thing. So in fact, there's a lot of attention given to this in the late 1990s. And actually, Congress passed a law that said that NASA should find all of these 100-meter asteroids with 90% efficiency. That law was passed in 1998. Unfortunately, it didn't come with any money. And so NASA just ignored it. And things went on that way. And eventually, the particular congressmen who were most concerned about this raised hearings in the House. They said, why aren't you guys doing anything about it? And NASA said, we'd be happy to do something about it. Give us a few $1 billion and we'll build a mission. Congress said no, and so it sat that way. Now, LSST, it turns out, will meet that mandate. Just all of these hundreds of pictures, we will find something like 90% of all the asteroids down to 100 meters for free at the same time as we're doing everything else. And we've testified on Capitol Hill that we would do that. The original congressional mandate said that NASA should do that by 2020. And unfortunately, this project is just starting construction now, so we're not going to do it by 2020. We'll do it more by like 2027. And so we gave this testimony to the House Science Committee, and the question we got back from the congressman who was most inquisitive is, well, what are we supposed to do for those 7 years? So this shows something about the understanding on Capitol Hill. Anyway, so this is an exciting area of science that comes from surveying. There's a lot of sort of more basic astronomy that will come from a project like this as well. In particular, we'll learn a lot about stars and how they evolve with time. Now, we've been observing stars in the sky since the dawn of time. And we know a lot about stars already. We have models for how stars evolve, how they burn up their hydrogen cores, and what happens afterward. But one of the things that limits that science is that the hardest thing in astronomy is to tell the distance to a star. You can measure how bright it is. You can measure something about its colors, which tell you its temperature, surface temperature. But it's very hard to know the distance. Every star is unresolved. And so it could be an intrinsically fainter object that's closer, or an intrinsically brighter object that's further away and would look the same. The new thing about LSST is that we will make these parallax measurements. So as I mentioned this earlier, parallax is the apparent motion that a star makes just due to the motion of the Earth around the sun. So as the Earth moves around the sun during the course of a year, it's physically moved in relation to the stars, and so the stars appear to shift slightly in the sky. The ones which are closer will shift more, and the ones which are further will shift less. And so if you can measure that effect, you can tell the distance. Now the problem has been that the atmosphere makes it pretty hard to make precise images much better than sort of an arc-second in scale. And the characteristic shifts of stars due to parallax out to sort of the edge of the galaxy are like milliarcseconds, a thousandth of an arcsecond. So it's very difficult to make that if you only have a few observations. But if you have 1,000 observations of every part of the sky, you have a lot of statistical data in which to use all that. And in fact, these parallaxes can be measured. So LSST will be the first ground-based telescope that will measure the distances to stars roughly to the outer part of the galaxy. And we'll look at figures which are like this. So what are you looking at here? These are plots of star clusters. On the vertical scale is a measure of how bright the star is. So each dot here is a star. And on the horizontal scale is a measure of the color of the star, which is related to its surface temperature. And if you look at these plots, you see there's sort of a dark stripe in most of them. That's what's called the main sequence in astronomy, and it corresponds to the track that stars lie on if they're in the dominant phase of their evolution, which is when they're burning hydrogen in their core. And so where a star sits on this track depends essentially only on its mass, a little bit on its chemical composition. Now you might notice in some of these that there's appeared to be a break. As stars complete their evolution, they complete the burning of hydrogen, they actually start to move off of that line. And so when you can measure a break like that, you can tell the age of that star cluster. And the interesting things about star clusters is that all the stars in the cluster formed at the same time. So plots like this are a way of telling the age. And they've been used in astronomy for many years to kind of provide tests of stellar evolution, of our computer models for how stars behave. The biggest problem with these kinds of plots is that since we don't know the distance to most of these stars, we can't really tell where to put this line vertically on the scale. You know, you could put, all the stars could be intrinsically fainter and closer, or they could be intrinsically more luminous and further away. And that's the biggest residual uncertainty in our understanding of how stars form. So this is a very old classical field of astronomy, but it will be revolutionized with these new data when we suddenly have distances to all these stars. There are other things that you can do if you can separate out the nearby objects in the sky from the more distant objects in the sky. In particular, you can start to remove a lot of the foreground light and pick up structures. So this is not a very clear picture, but it's taken from existing data. And this is a deep part of the sky. So these are angular coordinates, which just tell you this is some patch of the sky. And what's done in this picture is to sort of try to filter out, using the distances that exist today, all the foreground stars. And when you do that, if you sort of squint your eyes a little bit, you can see there are kind of streaks in this diagram. There's this thing, which is a very big feature in the Milky Way, but there are also these fainter streaks. Those are actually real features. What do they correspond to? They correspond to smaller galaxies that over the course of cosmic time have fallen into the Milky Way. Now, when a small galaxy falls into the Milky Way, there are tidal forces that tend to pull apart the stars that made up that original galaxy. And those stars are left in a trail, which is sort of permanently in the sky, which shows the trajectory of that smaller galaxy as it made its way into the Milky Way. And so by tracing out these kinds of structures, we can actually trace out the history of the Milky Way. The Milky Way is not a static object. It didn't fall at all one time. Over the course of cosmic time, smaller, more and more objects are sort of falling in, leaving these trails of stars, and increasing the mass of the Milky Way. So if you can do a survey like this, this is what we'll do with LSST. So this inner circle is roughly the size of the Milky Way galaxy. And this is actually a simulation, but it shows you what we expect to see. If you look at the outer regions of the Milky Way, you won't see this beautiful spiral. You'll see all these streaks due to sort of these tidal streams, that is what they're called, of previous galaxies that have fallen in. This is the current state of our knowledge. And this red circle corresponds to this dashed circle here. So we've been able to do some surveys in very small parts of the sky, and we can see small parts of concentrations, but nowhere near the whole picture. And with this white circle is for certain kinds of stars as far as we'll get with LSST. So we'll be able to trace out all of these structures that have led to the Milky Way's formation over time. And you can actually see these satellite galaxies themselves, again, doing this segregation on distance. So this is, if you look at a deep part of the sky, which is not, just a random part of the sky, every dot in a picture like this is a star. And this is what you'll see. It'll just look like a field of stars. If you segregate out on distance using the parallaxes or proper motions I mentioned earlier, then most of the foreground things go away, and you get a picture that looks like this. And if you smooth this picture to bring out the detail, you can see this concentration. So this is a small satellite galaxy which exists in the Milky Way. And there are thousands of these sorts of things, but they're very, very difficult to see because they get lost in just the stars themselves. So this is a sort of pattern that we'll be able to do.
Does it come in with a black hole?
No, the individual galaxies are just collections of stars. They're just much smaller versions of the Milky Way. Actually, they're dominated by dark matter. I'll come back to that later. Well, since we have 1,000 pictures of every part of the sky, we'll also measure not only things that move through the sky, but things that just change in brightness. And there are lots of things that change in brightness. Most stars are actually variable. They're not constant emitters that give the same amount of light all the time. The light varies in various different ways, both regular and irregular. There are large classes of stars which are called variable stars, and they're pretty much periodic. So their brightness goes up and down with a fixed period of time. We have a theoretical understanding of why that occurs. And so if you sort of take all the objects and you plot, the amplitude of the variation that you see as a function of the period in days, then you find these different classes of objects. They all have names. I won't go to what they're in, but obviously the sample we have to date is limited, and we'll go up to billions of stars with LSST, so we'll get a much, much more reliable statistical measure of this. And one of the things you can measure is the slight variation in the brightness of a star associated with a planet moving in front of it. Okay? Obviously, it's easiest to see that effect if it's a big planet and if that planet is close by. So the main kind of object you find doing this kind of measurement are things called hot Jupiters, which are planets roughly the size of Jupiter that are physically relatively close to their star, which makes them hot. Okay? And this plot shows the probability of us finding a hot Jupiter around a star as a function of its period in days and the size of the planet. And not surprisingly, for large planets which have short periods, so they're close to the star, it's easiest to find them. So and we'll find them with nearly 100% probability. And this is the particular distance at which we can find a hot Jupiter for sort of typical parameters. So this is probability of finding it as a function of the distance. And you can see for these kinds of hot Jupiters, we'll find them out to about 4 kiloparsecs, which again is of order the size of the galaxy. So we'll find all of these. But actually, one of the things that's more interesting about these timing measurements is not the sort of regular periodic effects that we know about, but the irregular aperiodic effects, which we're still learning about. Actually, we know very little about the intrinsic variability of the optical sky. We've made lots and lots of images of the sky over the course of human history, but not very many that are sort of frequent in time for the same part of the sky. And when you start to do that, you find things. So if you start to make regular measurements of parts of the sky, you find things like supernovae, which are the explosions of stars. There are two different kinds of supernovae, things that are called core collapse supernovae, which are very massive stars that have imploded on themselves, and things called type 1a supernovae, which are binary stars where a white dwarf, a degenerate star, has collected mass from its companion. And you can see other sort of things. This is a plot of the kind of characteristic scale of the variation as a function of the characteristic time scale of which sort of an outburst occurred. And there are various things marked on this. But most of this plot is empty, not because there's nothing there, just because we've never really looked. We've never looked for faint enough variations of stars on appropriate timescales to find these kinds of explosive phenomena. So this is the most likely area of discovery with LSST, things that go bump in the night, basically exploding objects on all different kinds of timescales, and hopefully with all sorts of interesting physical effects as well. So if you sort of take the population of variable sources, the things that can change in brightness, what are the relative populations? So this is sort of a pie chart on the left that shows you sort of what all the variable things will measure. And you'll notice 75% of the variations that we'll see in the sky will actually just be asteroids. So the things I was talking about earlier, but we know they exist. So that in and of itself is not terribly interesting. Incidentally, we will measure 10 million variable objects every night. So the biggest challenge in doing something with these data is not detecting the change. The biggest thing is, what do you do with 10 million objects? Okay. How do you analyze that set to find the interesting ones in the forest of more common ones? Most of them are asteroids. If you take out the asteroids, 4% are what we call stellar variables, the variable stars that I showed you earlier. Most of these are actually unknown asteroids. There's another 20% which are asteroids we already know about. And then the normal stellar variables. And only this tiny sliver, which is 1% of the pie, are these exploding things that we're most interested in. And if you break that out and say, what are they? Roughly half of them will be supernovae, the explosions of stars that we know about. Some will be what we call active galactic nuclei, which are black holes in the centers of galaxies that cause a lot of variations. Some will be novae, which are thermonuclear explosions on stars. And about 20%, we believe, are going to be things we have no idea what they are, just based on the statistics we have so far. Yeah, question?
What about comets? Are they too small to show up?
Comets are, they're much less frequent than the asteroids, but we're including them in the asteroids, just moving objects in the solar system. Okay, so that's sort of science that we can do in the solar system, science we can do in the galaxy. Actually, some of the most interesting stuff that will come from a survey like this has to do with looking well outside the galaxy, to the universe as a whole. And LSST will survey an enormous volume of the cosmos. So this is a plot of how far various different surveys have gotten in volume. This is volume of space as a function of redshift, which is a measure of how far back in time we're looking or how far out in space we're looking. Galaxies first formed, we believe, somewhere between redshift 6 and redshift 10. That gives you the number of 100 million galaxies that 100 billion galaxies that I talked about earlier, which is the total number of galaxies in the observable universe. LSST will get out to something like 10 to the 12th cubic megaparsecs. So this is going back to a distance which is of order 10 to the 12th years, roughly 10% back to the Big Bang. And so that's why we will actually record 10% of all the galaxies in the universe. This will be the first survey that will have detected or cataloged more stars and galaxies than there are people on the Earth. Every person on the Earth can own a star or a galaxy. You can have either one, or both. And you can follow the data on that object. That will be your very own object. I'll say a little bit more about that again later. So what do we do with all these galaxies? Well, we'll have deep images of the galaxies. And when you take deep pictures of the galaxies, you find some interesting things. And it's really important that you go deep. Remember earlier I said we have surveys of the sky that only go fairly shallow now. They don't go very deep. So on the right here, this is a picture. These are two pictures of the same galaxy. This is the same object. If you don't take a deep enough picture, you see a basic galaxy, which is a fuzzy blob. But if you expose longer, you start to see all these structures and the shapes. Those are the sort of tidal streams that I talked about earlier for the Milky Way. This is a more distant galaxy, but it had the same kind of history. Smaller objects fell into it in cosmic time. And actually how that structure behaves as a function as what other galaxies are nearby or what does that particular galaxy look like tells us a lot about how galaxies formed in the first place. And here's a particularly exotic one. This is a real picture. So you see the core, which looks like a normal spiral galaxy, like pictures of Andromeda you may have seen, but all this other structure. You would not see any of this unless you expose very deep. And that's why we need a very big telescope in order to get to adequate surface brightness to see a lot of these features. So we'll learn a lot about how galaxies formed and evolved. But there are other things we can do with the galaxies, which are related to a phenomenon called gravitational lensing. So you may have heard that most of the matter in the universe is actually not the ordinary matter we're familiar with, the kind that makes up our bodies or the things we're familiar with on Earth, or even the kind of matter we've made in accelerator facilities on Earth. Most of the matter in the universe is what we call dark matter. It doesn't interact in any known way with the stuff we're familiar with. What is this stuff? We have no idea. We're still trying to figure that out. We only know of its existence because it appears to exert gravity. So initially that was detected by looking at the orbits of stars or of other things, and we know that if the gravitational force is large enough, then the orbit of an object will be tighter. And so we can measure the gravitational field for various objects based on that. And we found there was appeared to be more matter there than we could account for by the light. That's what gave rise to dark matter. But matter also, or gravitation associated with matter, also can bend the trajectories of light. This came out of Einstein's theory of general relativity, which is our current modern view of how gravity works. And so if light from a distant galaxy passes through a concentration of dark matter, those light rays will be bent. They'll be distorted, just the way a normal lens works. Okay? So this is actually not a real picture, it's a simulation, but this is what a cluster of galaxies will look like, so a large concentration of dark matter. And these streaks that you're seeing are actually distant galaxies which lie behind that cluster. And as the light comes through that concentration of dark matter or that gravitational field, that light gets bent, and the images of those galaxies get stretched out and distorted just the way a lens would. And so if you can measure this kind of effect, and it's a statistical measurement, then you can determine how much dark matter was there. This is what's called gravitational lensing. And there are various limits of it. There are limits like this, where you see major distortions of the appearance of stars, and in some cases even multiple images of a single object. And there's what we call weak gravitational lensing, which is nowhere near as dramatic. You can sort of see it in this picture here. These individual objects still look like ordinary galaxies, but if you notice, their shapes are correlated. Okay, they're still kind of pointing in this circumferential direction. And it's that correlation of the shapes of background galaxies that tells you there's still a lensing effect going on in a concentration of gravitational matter. Now, this is these are real pictures, actually. This is a really spectacular result. It was discovered a few years ago. These both correspond to colliding clusters of galaxies, so very large concentrations of dark matter, which over cosmic time collided with one another. And the clusters of galaxies consist of both dark matter, which doesn't interact with normal matter or with itself, and gas, which is trapped in the gravitational field. So the blue here is the concentration of dark matter that we've identified based on using this gravitational lensing that I talked about earlier. And the red is what the gas is doing. So as these two clusters collided with each other, the gas interacts and gets trapped in the middle, but the dark matter goes right through with no interaction. And you see that on both of these objects. And it's in fact the separation between the blue and the red that tells you dark matter has to be really something different than ordinary matter, because in this collision, it behaved in a very fundamentally different way. It went right through, whereas the gas got trapped. So in fact, this kind of lensing can also tell us something about an even greater mystery in physics, which has to do with something called dark energy. This was discovered around the end of the 1990s, that the universe appears, we knew that the universe was expanding, but the universe appears to be accelerating as it expands. It's going faster, it's not slowing down. That was very much a surprise. Why is it a surprise? Because we know the universe is filled with matter. The matter exerts gravity on itself. And so as you have the universe expanding, there should have been a gravitational attraction that retarded that expansion. It should have slowed down with time, just as if you throw a ball up in the air. It can start out with high velocity, but it'll slow down as it reaches its peak. But in fact, we found that the universe is accelerating. It's not decelerating. And that means that's actually not incompatible with Einstein's theory of relativity, but it requires that the entire universe be filled with some kind of mysterious energy field that has negative pressure. And we have less than any idea of what that stuff is. Okay, this is one of the greatest mysteries of modern physics. And all theoretical physicists around the world are focused on trying to solve this problem. Now, what does the survey tell us about it? Well, the way we can get a better handle on this is to chart with increasing accuracy how the universe actually is expanding with time. And one way of doing that is to look at what we call the growth of structure. The universe started out very homogeneous, very uniform. But as it expanded, because gravity is an attractive force, small concentrations of matter attracted other concentrations of matter and grew with time. This plot sort of shows that with these gray things. So as you go very far back in time, you see sort of a uniform concentration, but as the universe expansion goes on, these sort of concentrations of dark matter get larger and larger. Now these sort of tube things here are meant to be bundles of light rays coming from background galaxies. And as those bundles of light rays pass through those dark matter concentrations, they get bent, as you can see. And bundles of light rays from nearby objects in the sky get bent in similar ways. And that yields a correlation in shapes. It's a very subtle statistical effect, but it tells us how the growth of structure occurred as the universe expanded. And that gives us, it turns out, what will be the tightest constraints on really mapping the expansion history of the universe and the most constraining results for theories of dark energy. Okay, in the remaining time I have left, let me just tell you a little bit about the telescope itself. This project is a large, complex system involving a very big telescope in sight, a complex network to transfer enormous volumes of data back to our computing facilities in the States, what will be the largest digital camera ever constructed, and there's an education public outreach aspect of this. How do we convey the excitement of the sky to the public as a whole? The telescope will be sited on a peak called Separabon, which is in Chile. We've actually already leveled the site. This is where the main telescope will go. And there's a subsidiary hill here where we'll put a calibration facility. This is what the facility will look like. It looks a little bit like an ocean liner. Okay, strange. That's actually not an accident. In taking images of the sky from the ground, the biggest limiting effect is the turbulence in the atmosphere, which tends to shake those images around. And so when you design your facility, you want to ensure that you've generated as little turbulence as possible around where the telescope is. So in fact, on this particular site, the prevailing winds go in this direction. And so we put the building over here, and all of the heat dissipation and the energy and the motors and all that stuff is in this part of the building. So the air has gone, when it gets over that, it's already passed by the telescope. And that will leave a sort of laminar flow around the telescope, which should yield very clean images. The telescope itself is also very unusual in design. As you can see, it's kind of short and squat. It doesn't look like any telescope you may have seen before, particularly big telescopes. The reason for that is that we're trying to take pictures every 15 seconds and then step around the sky very quickly. We can't spend a lot of time waiting for the telescope to settle down after we've gone through. So we needed a very stiff design, one that could very quickly go to the next place. And the requirement is that we're ready to take the next picture within 5 seconds of having moved to a new part of the sky. The optical design for the telescope is also very novel. So this is what the path looks like. The light comes in and hits a primary mirror, which is an annulus with a parabolic surface. That's then reflected to a secondary mirror, which is convex, on into a tertiary mirror, a third reflection, and then on into the camera. And there are 3 lenses in the camera that focus the light. Why is such a complex design? Nobody's ever built a telescope like this before. It's because we had to get this very wide field of view. And as you go on axis with a conventional mirror, you get very clean images. But as you start to go off axis, you start to get aberrations due to coma and astigmatism and other sorts of optical terms. In order to cancel all those aberrations, you need to have at least 3 bounces. And that's why we did this design. And in fact, the mirror, the primary tertiary, is something we've already fabricated. So this is the mirror, and you can get an idea of its size from all the people standing around it. And you can see the break here between the primary surface and the tertiary surface. And this was a real technical challenge because those two surfaces have to be coaxial to within millimeters. And as we do this precision policing, we have to really know where everything is. So this was a real technical achievement. This is the camera. The entrance lens of the camera will be 5 feet 5 inches high. Our project manager for this project is a woman named Nadine Carita. When she joined the project, she changed all the male stick figures to female stick figures. And she is also exactly 5 feet 5 inches high. So she likes to point out that the entrance lens of the camera is as big as she is. It weighs 3,000 kilograms. It's about 10 feet from front to back. Lots of complexity in the middle. And as I mentioned, we're building this with these very high-tech electronic detectors. They're large, they're very sensitive, and we got to put them very close to each other. So there's a gap between these two sensors, which is about 100 microns, 1/10 of a millimeter. And we're trying to do that because we want to cover every part of the focal plane and not lose any light. If those two sensors touch, we would destroy both of them. And they're $100,000 a piece. So we've got to be real careful in how we assemble this focal plane. And then what may be the most interesting challenge on the project is actually just dealing with the data. LSST will generate something like 30 terabytes of data per night. Over 10 years, the total database will be 200 petabytes or so. That's comparable to all the world's current information, everything that's ever been written in any language since the history of civilization. The catalog alone, it will contain all these stars and galaxies and the sightings of them, will be trillions of lines long. That large a data volume actually breaks current database technologies. You say, how do you find something in a catalog which is trillions of lines long? How do you do that in a reasonable period of time? That's challenged some of the greatest minds in computer science, which we have working on this project. And we've had to invent new technology. So this was big data before the words became fashionable, actually. And it will be it's one of the nice spin-offs of the project that it will tie into some other things that are happening. And these are sort of computing requirements. It turns out that if you follow Moore's law, LSST at the time we build our computer center will be roughly there. This top line is the fastest computer in the world. This is the 500th computer in the world. We'll be somewhere there. Not particularly challenging because of the advances with Moore's law, but still a very big computer facility. And maybe one of the most interesting things about LSST is its connection to the public. So we're really thinking about this in a far-sighted way. All of the data from LSST will be available to everybody. Not only professionals, amateurs, children. We can give a galaxy to every school in the world. 250,000 of those galaxies per year will have a supernova go off. So if the school kids every day look at what's happening with their galaxy, 250,000 schools will actually find a supernova. And in most cases, those kids will be the first humans on Earth to look at that image. So it's a direct connection to the natural world and to the sky that something like this enables. And in fact, we have an ambitious program of what we call citizen science. There's lots of ways in which the public can not only be aware of what we're learning, but actually directly participate in it. And there are already some pilot projects along those lines that will continue with LSST. This project is distributed all over the US. This is a slide I made for a talk I gave in Washington, shamelessly pandering to senators from various different states, but just pointing out that the people we have working on this project come in all shapes and sizes, and they live all over the United States. And let me close there. Thanks very much for your attention. What?
Where is it going to be built?
It will be built, did you say when or where?
Where?
In Chile. I mentioned that earlier. So it'll be in northern Chile, which is a well-developed astronomical area. Yeah, question over there.
So we've been imaging the Andromeda Galaxy for about 100 years or so. What would
Right.
happen if we were to layer in a sequence over time those images? Would we see anything?
So we have produced very deep images of Andromeda, and we have detected a lot of variable objects in Andromeda. So Andromeda is one galaxy. It contains lots of variable stars, just like the Milky Way. You see all the different populations we see. We've seen supernovae in Andromeda, and we've seen supernovae in other nearby galaxies.
Like any actual movement, some of these satellite galaxies, not enough timescales to see that.
They're very faint. You really need to, so when you do very deep imaging, you can see some structures, but you don't see the changes. You can see the remnants of those satellite galaxies that have been interacted with Andromeda. Yeah, in the back.
How long will it take to build, and when do you expect it to be completed?
So we're limited by funding, maybe not surprisingly. We're supposed to start construction this year, and the telescope will be completed in 2019. And we'll have the first images of the sky using it in roughly 2019, 2020. We had a short hiccup last week because in order to start the construction, you have to have what's called a final design review, which is an in-depth review of every aspect of the cost and the schedule and the technology. That was scheduled for next week, starting Monday. Unfortunately, because of the government shutdown, that's been postponed. So we're hoping we'll get that back together by December and hold schedule, but that's what's actually limiting us right now. Yeah.
Why did you pick Chile as the place to put it?
Chile is an outstanding astronomical site. It's a high site. It's very dry. There are a lot of telescopes there already. There's a fair amount of infrastructure. But you want is a site which has good seeing, little turbulence. You want it to have pretty much cloud-free nights most of the time and low water vapor. And so we did a careful study of all potential sites on the Earth, and this was the best. Yeah.
So it seems like this project has something for everyone. Did it grow out of a particular, like, a desire to study dark energy, or did everyone just say, this is what we need?
So as I said, the idea is really kind of simple. So it's not, it didn't take a genius to say, let's make a big telescope and survey everything in the sky. And it was obvious that would affect a lot of science. There was a particular drive for cosmology to get a large sample of galaxies, which is relevant to dark matter, dark energy, but also for the solar system studies. And what was a bit of a surprise, and we were not aware of this ahead of time, is that you could actually do all of these different science investigations with essentially the same facility. And not only the same facility, but the same observing pattern. So that was news to us, and once we actually got it designed, we found out that was true, which is a great synergy. We call it massively parallel astrophysics. Yeah, question there.
Given the global significance of this project, why was the funding primarily funding from our own national resources as opposed to global resources?
Yeah, so it's a very good question. So there's a huge amount of interest internationally in it. In fact, I was in Europe just a month ago, arranging with various parties, both in Asia and Europe, about what their involvement with. There will be significant contributions from the rest of the world to the operations of the telescope, but actually it's preferable to us to build it with US money alone. It's actually easier to do it as a US project and not have to deal with the politics of getting everybody on board of where we are than you gain by having the co-contribution. So we're interested in the international contributions for the operations, but not for the construction. My current guess is that well over half the users of this telescope will be foreign when we're finished. But science works that way. For these big projects, everything is global. The discovery of the Higgs boson was done at the Large Hadron Collider in Europe. Americans had a lot to do with that. And so these various different projects are done by different parts of the world for the benefit of everybody, and that's what we're after. Yeah, over here.
10 years seems like a long time to a funding agency. Is it possible that dark matter and dark energy have very different timescales? And I ask that as a geologist. The eruption of a volcano and the cooling of the magma body is about a million years.
Right. So you're right. The behavior of dark matter and dark energy are not going to change on 10 years. What we're not going to see an evolution there. What we're hopeful is that the statistical constraints we'll get from these billions of galaxies will have helped our understanding. Now, how much progress we make depends on what dark matter and dark energy really are. And that's the mystery. We don't know. Some of the other things that I talked about where you're seeing real variations in time, those have natural timescales, but they're unrelated to the fundamental cosmological issues. Yeah. In the back?
Would you explain why the gravitational lensing seems to be circumferential rather than radial?
Yeah, well, it turns out that the two if you have a spherical concentration of matter, the symmetry alone tells you it's either circumferential or radial. And it's circumferential for a positive excess of matter, and it's radial for a hole. Okay, so there are two possibilities, and the signs work out that way. I don't know if that's an adequate explanation. But yeah, over here.
You talked about, at the beginning you talked about southern sky is what you would observe with
Right.
LSST. But you're capturing information about all the asteroids. Is there no information about the north, or is there a
Yes. So we're limited just by geography, right? We sit on a mountain in the southern hemisphere, and there's only a limited part of the northern hemisphere that you can see at not too large an angle from the zenith, which would affect the results. But fortunately, the ecliptic plane, which is the plane of the solar system, actually runs across the two hemispheres. So over the course of these asteroid orbits, they almost all intersect. So if you cover the ecliptic well, you can get up to 80–90% completeness, even by only covering half the sky. Yeah, in the back.
You showed the one graph on logarithmic mapping. Either you could look at a large part of the sky, or you could look at very dense stars and form this one line. You were way off the line with this, but what technological breakthrough really allows you to do that?
So three things. That's what I tried to emphasize at the end. One is we needed the technology to make a large telescope that had no aberrations out to a large field. And that required this multi-bounce mirror, which had never been done before. Secondly, we needed to build a 3 billion pixel camera with a focal plane which is this large and CCDs. And it's only in the last few years that that's even been conceivable. And then finally, we needed to be able to analyze hundreds of petabytes of data. And that's also new technology. So none of those three elements really would have been possible in the 90s, and they've become possible over the last 10 years. So that's what's really new about it. Yeah?
Can you comment on the radio telescopes as opposed to the optical telescopes? Do you interface with one another, or are they entirely different thing? Or
Yeah, so the electromagnetic spectrum goes from very long wavelength radiation in the radio to the highest, shortest wavelength or highest energy radiation like gamma rays. Each of those different parts of the spectrum convey different information. Normal stars emit mostly visible light and infrared light, and that's what we're looking at with LSST. They don't emit a lot of radio light. Clouds of gas emit radio light, and other sorts of accelerated particles and things. So they're really quite complementary. And in fact, our understanding of basic processes in astrophysics over the last 20 years or so has come because we've made observations across the entire electromagnetic spectrum. So these really serve different purposes. They're not redundant. And the information together tells us things. There are certain things which are only visible in the radio band, but most astronomical objects are visible in the optical band, which is why that still remains the mainstream of astronomy. Yeah, let me take this one, maybe two last questions, because I think we're running out of time. Yeah.
What's the bandwidth that you're going to be able to observe? What kind of detectors?
We'll go from about 3,000 angstroms out to beyond 1 micron. So 3,000 angstroms is the bluest that your eyes can see, and we'll go out to the near infrared, which is about 1 micron radiation. So that's a very broad band. And the desire to cover a very broad band had major implications for the detectors and also for the coatings on the mirrors and things. Yeah?
Of all of the questions that this telescope might answer, which is the one you are waiting to answer?
So I like tough questions, personally. So what motivated me to work on this was actually trying to figure out what dark energy is. And partly, it's not just that that's such a fundamental mystery. It's that the measurement is extremely hard. That sort of gravitational lensing effect I talk about, we're looking for a departure from circularity of like a part in 10 to the 7. in a statistical way. In order to be able to measure that, we better understand what the atmosphere is doing, what the telescope's doing, what the camera's doing to very high precision. So to make that kind of measurement requires building the thing, understanding exactly how it works, modeling it, and also understanding the cosmology itself. And I like that whole integrated picture, so that's what motivates me. Okay, let me stop there. Thanks very much for your time.